Hello, class. So on this video, we're going to start with a new topic. We're going to start talking about the general solution of an ODE. It's something that I kind of slipped, from my mouth last time in a couple of the previous videos. I didn't want to talk about it yet as a formal definition, but I'm going to do it in this part of the videos. Now, if you're following the book, which, like I mentioned, following the book is a very good thing to do because it's good supplemental information to what I'm doing here in the lectures. If you're doing that, or if you want to do that, we're in section 1.2. So chapter 1, section 2. What I covered in the previous video is, I guess you could say, is chapter 1, section 1, but it's basically just a general introduction to ODEs. So if you want to start following the book, I will start doing it now. And again, we're starting in chapter 1, section 2. Now, before we start talking about this, let me say a couple things from what we did in the previous videos. There's one thing for you to mention, to take notice of. So in the previous video, we were working with this model, dv dt times m, where m is mass equals negative mg, where g is acceleration due to gravity, equals kv. Where k is a constant, specifically the drag coefficient, this comes from the air resistance. Remember, this was giving you the velocity of an object in free fall, right? So an object falling from some height in vertical one-dimensional motion, and assume that the only forces acting on the object were its weight and the air resistance. Now, in the previous video, we did this example where we assumed that there was no air resistance. And then what we got from that is that this model simplified to m dv dt equals negative mg. Since m is not equal to 0, we can divide both sides by m, and it basically is simplified to dv dt equals negative g. Now, what did we do when we were finding the general solution? No, okay, there, I want to say general solution again, so let me just get to it soon. What did we do here? We're trying to find a solution, and what's the general process that we know for finding solutions? Well, what we do is that we integrate both sides of the differential equation with respect to t. Again, we integrate with respect to t because that's the variable we're taking the derivative with respect to. That's the independent variable. Now, what I want to mention about this is, what is a solution to this differential equation? Well, a solution is a velocity function, right, that satisfies this equation. Okay. Now, remember that we know from calculus that every time you integrate, you end up with a integration constant, right? You always end up with a plus c. So what happened in this case, in this example, we integrated once, right? So we integrated once to find velocity functions. Again, solutions are functions that satisfy this equation. Based on the context, they are velocity functions. So when we integrated, we got this integration constant. How do we get rid of it? Well, we needed an initial condition, right? And we used the initial condition with, I think specifically was v of 0 equals 1. The initial velocity equals 1. And how did we use it? We used this initial condition to get rid of the constant. Now, in that problem, we weren't only looking for velocity, we wanted to go even further and find position. So given velocity, how do we find position? We integrate it again. Why? Because if you integrate velocity, you get position up to a constant, right? So we're doing an indefinite integral. Now, since we added, every time we integrate, we get a new constant of integration. When we found the position function, there were infinitely many of them, right? There was a plus c somewhere. So what did we do? We used another initial condition. And I think for that specific case was S of 0 equals 100. So the position of the rocket times 0 was 100, right when you either dropped it or pushed it downward. And what I want you to notice is, or what I want you to take, what I want you to take out of this is that basically there's this relationship that depending on how many times you need to integrate a differential equation in order to find a solution, that's how many initial conditions you're going to need to get rid of the extra constants. So it's basically what I want you to take away from this. So basically, if we integrate a ordinary differential equation, let's say n times, to get a solution, well, we integrated n times. That means we got n arbitrary constants. How do we get rid of each arbitrary constant? For each one of those, we need an initial condition. So then we need n initial conditions to get rid of the integration constants. Now, this is going to be very important, especially when we start looking at differential equations where we have derivatives of higher order. Like if our differential equation has the third derivative of a function with respect to a variable, right? Then since we're taking the derivative 3 times, we're going to have to integrate 3 times. So we're going to get 3 different arbitrary constants. If we want to get rid of them, we're going to need 3 initial conditions. So that's basically the idea. Okay. So just a note that I wanted to do about a pattern that came up in the previous video or videos. Now let's talk about the general solution of an ODE. Now, again, I'm going to go back to a very easy example that which we already did. So when we had the differential equation, dy dx equals 2, what did we do to find solutions? Well, we just integrated both sides with respect to x. So integrate both sides with respect to x. An antiderivative of dy dx is y by definition. So left-hand side becomes y plus a constant of integration equals 2x plus another constant of integration. I mentioned that anytime you have two constants of integration, you can just combine them into one arbitrary constant of integration. So subtract c from both sides, rewrite d minus c as just a new constant c. This becomes 2x plus c. Now, notice that here, a few things happen. We know that functions of this form are going to be solutions. We saw that before in the previous video. Not only that, but based on the method we did to find this family of solutions, we basically integrated both sides and worked from there. What that means is that it's not only the case that solutions of this form work, there are solutions, functions of this form are solutions. It's also the case that if you have a solution, it has to have this form. And again, this is required because we're solving this differential equation by integrating. And this basically follows from the fundamental theorem of calculus. Any two solutions are going to differ by a constant. So what that tells us is any solution that for this differential equation must have this form, 2x plus c. That is what we call a general solution to a differential equation. So let me write that as a formal definition. So definition 3. I believe that my numbering, the way I'm doing it is I'm going to do numberings not following the book, just following my notes, and I'll restart the numbering each chapter. So we already had definitions 1 and definitions 2 in previous videos. So this is going to be definition 3. So the general solution for an ODE is an expression that contains all possible solutions. So again, y equals 2x plus c would be the general solution of the differential equation dy dx equals 2. Why? Because any solution is going to have this form. Right? So that's precisely what a general solution is, an expression that contains all possible solutions. Let me add to the ODE. So that's what a general solution is. So now, every time I say find the general solution for a differential equation, I want an expression like this, something that contains all possible solutions to the differential equation. And again, based on the fact that we're finding these solutions by integrating, the fact that we're using this method guarantees us that what we're left with is the general solution. Okay. So now in the next video, I'm going to show you how to find the general solution of a specific family of differential equations, and then we'll see another model. We did a model of a falling object, and we're going to do a model of population growth. They're kind of classic differential equation models.